Ready? Okay. Hi, everyone. I'm Molly Gaines. Thanks for coming to the CGA, Center for Geospatial Analytics Geospatial Forum, introducing Dr. Christa Brelsford. She's a research scientist at Los Alamos National Lab in New Mexico. And before that, she was the Leanne Russell Fellow at Oak Ridge National Laboratory, and before that, a postdoctoral fellow at the Santa Fe Institute. She earned her PhD from the School of Sustainability at Arizona State University for research on the determinants of residential water demand. And Christa's core research focuses on developing empirical methods to understand interactions between human and physical systems, especially in urban contexts. For some personal background, I first met Christa as an undergraduate intern at Oak Ridge National Lab in 2018, and we worked together on a project focused on heterogeneity and scale of sustainable development in cities in South Africa. And her mentorship and encouragement, as well as learning more about scientific research and the National Lab system, is really a big part of what inspired me to pursue a PhD. So big thanks to Christa for that. And Christa continues to do really interesting and inspiring work, and I'm excited for everyone to learn all about it.
Cool. Thank you, Molly. Yeah. Hi, folks. Thanks so much for having me. Some students like Molly are ones that you have to keep, they're so good, you just have to keep track of them for a while. It was a pleasure working with Molly all that time ago, and it's so much fun to be here and see a bunch of new students. Yeah, as Molly said, I'm Christa Brelsford. So I'll start this talk by request with a sort of short introduction to who I am as a human being, and then talk about some of my work. I'm talking about what will eventually be more or less two papers. The first paper is a little half-baked because I thought it was more interesting to give a talk on work in progress. Both then maybe I'll learn something because some of you will probably have interesting ideas about what I could do with the work. And it's just more interesting because it's what I'm actively working on. And then the second one is a paper that was just published a couple of weeks ago, focusing on how we understand risk to people from flooding. Good? All right. So starting at the very beginning, I was born up in Alaska, in Anchorage, fairly rapidly as a toddler moved to Aniak, population like 80, 200 something, very, very small off the road system. Then moved to Dillingham, much bigger with a population of 3,000 or 4,000 in the wintertime. Dillingham is not known for much other than that's where 80% of America's wild-caught salmon comes through. Then in late elementary, moved back to Anchorage, and then started college at Simon's Rock College in Western Massachusetts. This is another little tiny college that mostly takes younger students. Went on to get the rest of my bachelor's degree in civil engineering at Columbia, a master's degree in climate science, and then jumped back west to go to the school of, as Molly said, to go to the School of Sustainability, focusing on residential water stuff. But before I finished my PhD, in the first year, halfway through the second year of my PhD, I was in Haiti during the earthquake in 2010, and a house fell on me, which is how I earned my prosthetic leg. So that was an interesting interlude in the beginning of graduate school. Then, did a bunch of water management work. Arizona's a desert, if you've heard. So focused on that for my PhD. Moved to New Mexico, partly because I really liked the rock climbing there, but also Los Alamos National Lab was there. So as a graduate student, I was back and forth between ASU and LANL quite a bit, working on my PhD, both through school and through the National Lab, and then did a postdoc at the Santa Fe Institute, which was nearby. When I finished my postdoc, I took a fellowship at Oak Ridge National Lab, and over the course of the time ended up with all these little creatures, including this very important collaboration between my husband and I. I earned first author for all of these. They're bigger now because I put that graphic together in 2020 when my spouse and I's first paper together was published. And then about 2 years ago, we moved back from Oak Ridge National Lab to Los Alamos National Lab. That's what we all look like well, about 2 years ago. I couldn't find a picture of all 5 of us recently. Yeah, and so now I'm a research scientist at Los Alamos National Lab. So I've spent most of my career in the DOE system. In this talk, I don't have sort of official slides on what it's like to be a DOE scientist as opposed to a university scientist, but lots of you had questions about that at lunch. If you have more questions when we get to Q&A, feel free to ask. Okay, now for science. One of the ways that I think about the work, I've always structured the work that I do to the extent that I can to try to do work that contributes to a better world. And that's one of the reasons I like the national labs. In their best iteration of themselves, they're very application focused, very focused on doing work that matters. And for me, much of that time has been understanding climate. So sort of one way of thinking about interactions between climate systems and human systems is that we've got all these global high resolution models of the climate that are so coarse that people in cities like don't even exist in them. As we're getting towards more high resolution models, models at the scale of a river basin are flat wrong when you forget to include infrastructure and land cover. And so sort of infrastructure, land cover, cities, and the technology that we use to shape the world is one of the most significant ways that I think it's reasonable to think about how climate systems and human systems interact from a computational or modeling perspective. And when you think about infrastructure and land cover, what is infrastructure and land cover determined by? Demographics, socioeconomics, resource demand. These are the kinds of things that drive outcomes in infrastructure. And so this sort of is a chain. I have lived most of my academic life about here, but I talk to people over here and I talk to people over there too. And cities specifically are fun because they are sort of concentrators of systems across sectors, across scales. Everything in cities sort of happens a little faster than in other places. And that's one of the reasons that I've ended up sort of calling myself a cities person for many years. If you want, I'm very used to sort of a call and response. So if you have any questions or you want to stop me, feel free to raise your hand. I like it when people talk back to me. Okay. So sort of the sort of core goals in the way I've structured this talk is thinking about how do we understand urban heterogeneity, right? Heterogeneity is a fundamental component of cities. There's no city that is uniform in how and where people live, in economic activity, in how dense it is, in where the buildings are, in where the parks are, in where the whatevers are. Heterogeneity is a fundamental component of cities. But we don't have really good systematic ways of measuring exactly what we mean when we say heterogeneity. Or harder yet is how heterogeneous is Raleigh going to be in 20 years? I don't know. We don't have theories on that, even though we know that it will be heterogeneous and probably more heterogeneous in the future than it is now. But exactly how much and what the right ways to measure that aren't really well supported by theory. Even though there is really good evidence that there exists fine-scale spatial patterning in urban infrastructure. So here's a handful of papers that are sort of using AI-based methods to try to forecast how cities are going to look in the future. And I don't think, this is a cute paper by a colleague of mine that I helped with that's trying to predict building height from building footprints. And the reason I'm putting this up here is not because this is the world's best paper, no offense to my colleagues, but because it's evidence that there is structure, that nonlinear AI models can learn the structure and predict on it. So hopefully someday we can get to where we can, in a theoretical, in a pattern-based way, actually understand the structure, not just have a computer that can sort of see some patterns in it. Here's another paper. I've been talking about this a lot to folks here because this is the method that I am presently testing against futures to see how we think they behave. This is a land cover using AI diffusion model to forecast land cover. So it's very atheoretical. It doesn't have any kind of sense about how we think urban growth happens. But it's using the same kinds of things that the internet is using to make cat videos. So it's sort of reassuring to me to see that it stands up that there's quite a lot of concordance between this model's output and futures. We can also, there's also sort of strong cluster, if you just look at urban imperviousness, this is Moran's eye against urban population. And in one way, overall, cities that are bigger have this is a geography. Do I need to define Moranzai? This is a geography department, so I don't want to treat you guys like you don't know stuff, but I can define it. Define it? Okay, all right, I'll skip it then. All right, so there's more clustering in bigger cities. Bigger cities have more clustering than smaller cities. But as time goes on, the amount of clustering in all the cities sort of goes down. And that suggests that there's two different generating processes, right? Otherwise, you wouldn't get that orthogonality in the relationship between space and time. I don't yet know what's causing that orthogonality, but because I can see the pattern, it's something interesting to me. Here's another way. This is what Molly worked on. It was a long time ago, but Molly helped me with some of this work back a while ago. Here's one way of trying to characterize heterogeneity in space in urban environments. The paper that we first published it on was about infrastructure. We've also later on applied it to a bunch of different things. But the basic idea is it works for any metric that you have geographic information on that's bounded. And then to make the math easy, you rescale it to between 0 and 1, just so that we don't have to think about heights. And then also it works for understanding when your geographies are nested. So neighborhoods within cities, block groups within census tracts, cities within regions. As long as you've got a hierarchically structured geography, which is sort of how we understand most things, it works. And then you can measure the value of your thing, access to infrastructure, education levels, wealth is functionally unbounded, so that one's tricky, nighttime lights. It works for lots of things. You measure the value of your thing in your neighborhood we'll go with neighborhoods and cities to have two levels for now. In your neighborhood, and then you find the population weighted mean, and that gives you some value here. But standard deviation is structurally bounded when your original measure of interest is bounded. So the maximum possible value you can get, if your distribution of your whatever is as unequal as possible, is going to be on this line up here that we can write down because math is fun. And so what that implies is that for any given average level of access to your service or your thing, there's a maximally unequal level of how unequal things can be in your city that we can write down, and then we can define the level of inequality as sigma over the maximum value. Then you can color it like this, and it looks nice and pretty, right? So down here, your resources is pretty uniformly distributed across the city. Up here, it's as unequal as it can be given the level of resource. If everybody has all the things, there can be no inequality. Similarly, if nobody has anything, there can be no inequality. And then we've applied it to a bunch of stuff. Don't forget about this one. We looked at access to urban services in Brazil and South Africa. Again, Molly was looking at how access to urban services in South Africa changed between the 2001 and 2011 census. Just at lunch, we were like, maybe we should look up 2021 and finally publish this paper. Another very, very smart student spent a very long time collecting Indian census data to sort of apply the same framework to India. And then also for imperviousness across MSAs and across the cities. There are dots here that apparently didn't make it. So sort of that's the broad framework over which I've been thinking about urban heterogeneity. And then specifically, this is the bit that's a little half-baked, so I really, really, really welcome your thoughts and questions and comments. It's what I've been sort of working on quite a lot the last couple of weeks. It's a lot of fun. And this is a proposal I wrote with just one postdoc, where the goal is to sort of link up what we know about urban scaling theory with data that we have about social interactions to test the constraints underlying the theory and then hopefully do some good. There exists a theory of cities called urban scaling theory. Molly's heard of it, but probably nobody else has. Okay. And the basic idea behind this theory, this is sort of the 2010 paper that sort of first presented it, that there's a very strong systematic superlinear scaling relationship between a city population and a whole bunch of different socioeconomic outcomes of cities. And this is measured at the average level. So each of these dots here represents one of these metrics for one, in this case, United States city. And they all scale just like this, where the beta exponent works out to be about 7/6. Because I will work through this. Have you seen this before? Okay, so that's sort of the basic theory, and it's been tested for infrastructure, which scales sublinearly with a 5/6 scaling exponent, and socioeconomic quantities, which scale superlinearly with a 7/6 scaling exponent. They've been shown around the world. This is a test in South Africa and Brazil. This is other colleagues who worked on it across European cities for a bunch of different metrics, and then also this is one paper. Looking sort of back to sort of not prehistory, but the Toltec and the Aztecs, so sort of back throughout history too. So this theory is proposed to be a very, very general characterization of the relationship between city size and a bunch of socioeconomic outcomes and infrastructure. Questions, thoughts? Okay. Another way that, and underlying the sort of the cartoon version of the hypothesis that supports this theory is that interactions between people generate novelty. So when I interact with you, I learn cool new things about futures or cool new things about all the other stuff that's going on. And that is a product of an outcome. And maybe we'll get to have a collaboration and have a new patent or whatever ways that the novelty generated by our interactions sparks something new. When you do a literature review, a lot of different fields have characterized, so to draw cartoons about academic disciplines, urban economists often think of cities as sort of a well-mixed bag of interesting people. Urban planners might think of locations as functions of interactions. Engineers think of infrastructure as sort of the fundamental underpinning of a city. And then complexity people often abstract away a lot of the details of infrastructure and space and socioeconomics to a very, very general level. But fundamentally, all of these different disciplines are in one way or another saying that interactions between people are one of cities' most fundamental characteristics. And so this project that I'm working on is trying to then actually test that hypothesis. What do we learn about cities when we can measure interactions? To be a little more detailed about how Betancourt's 2010 theory works out, his approach is organized around population level averages, right? Everything that I showed you before, each dot was a city. That this is the average population, or the measured population for the city, and the average, or the total GDP. It was total GDP, total crime, and total volume of infrastructure. And he only, and when Betancourt wrote this paper, he was saying interactions are what are driving all of this. Infrastructure exists to enable the circulation of people, goods, and ideas. So what I'm trying to do in this proposal, in this sort of current project, is get down to the level of interactions rather than city level averages. The sort of specific way I'm doing that is when he wrote his models, he put everybody in the roads. All in the math that Luis worked out. All interactions and all things in cities only happen on the road system. And that's a sufficient approximation, sort of, but I'm trying to do better. That's the goal. Yeah, but interactions have been wildly costly to measure at scale, but I got some super cool data from Oak Ridge National Lab. Yeah, so some of the genesis of this project was when I was at Oak Ridge National Lab, and we didn't get time and funding to work on it until I left. But Oak Ridge has been working with a commercial data aggregator and providing them with sort of billions and billions of mobile device location records per day. And then they, in their own world, clean and process it, and they create a bunch of different outcomes. But what they give me is a matrix of device co-location. So when you're and my phone spend sufficient time together in the same place, that counts as a co-location. Now, being in the same place isn't necessarily an interaction. I go to a coffee shop and sit next to lots of people I don't talk to. But it's a necessary condition to have a face-to-face interaction. Yeah, so in sort of cleaning the data, they're included in the data set. If a device is included in the data, if it's got data on at least half the days of our study period, and we're requiring they be at a stop location, a point point of interest for the same 60 minutes, which is kind of a long time. And stop locations are sort of 30 meters, just that's how they constructed the data. So it's got 400 times more people than any previously available data set, which is huge. It's still only a 2 to 5-ish% sample of the population of any given city, which is on the one hand enormous, and on the other hand still kind of too small to say good things about network statistics. If we weren't worried about the network aspects of it, then 2 to 5% of a city would be great. But networks get weird when you sample them. So I asked for data from 10 cities, specifically chosen to have a uniform distribution across the population of cities in the United States, so that if you just randomly sample cities, we'll only get the little ones, right? And if we only look at the big ones, we won't know what's going on in the little ones. And because scaling theory is about how things change as a function of city size, we got a nice uniform distribution of cities across the space of urban populations. So this is in Comic Sans because it is half-baked. Because imagine I'm writing it on a chalkboard. I'm still figuring this part out. So I very much invite comments. Some of the things we know, so the things that are in blue are things that I think are a function, that are scale with city population. N is what I'm using for city population. And some of these are constants that are time constrained. So there's good evidence in the scientific literature that people around the world and throughout history tend to travel for about an hour and a half a day. We get miserable and we get unhappy if our commutes and all the things that we need to do to live are longer than an hour and a half. And that makes sense, right? Because like we can be different in a huge number of ways, but we all have the same 24 hours in a day, and the same sort of biological needs for sleep and so on. So the sort of physical constraints on travel time make a lot of sense. And in this version of the world, we're treating that as a fixed constant. For the same reason, we're proposing that the amount of time one spends in public is also fixed. But we know, or the literature suggests, that urban area is a strong function of N, of city population, right? Like as cities have more people, of course they have more area. But also there's a systematic relationship that as cities grow, they also become more dense. So when a city doubles its population, it doesn't double its area. It grows by sort of population to the exponent for the relationship between urban population and area is 2/3. Similarly, points of interest, I'm using POI as an abbreviation for points of interest. That's sort of anywhere you'd find on Google Maps. Similarly, we believe those scale. So sort of the vision here is that all of these will sort of eventually add up. And I'll be able to write down an equation for how I think the instantaneous population of people in interesting places scales with city population. And that will give us a theoretical expectation on the scaling of interactions between people and city size, with the hypothesis that in a bigger city, you ought to have more interactions per capita. I don't have this sort of fully written down. I've done some bits and pieces of it, but I don't have the sort of full equations yet because I haven't gotten there yet. So here's one way that I'm sort of trying to write down how I think travel speed scales with city population. We've got I said before, right? Like I think everybody, on average, people spend an hour and a half a day traveling. So the travel distance must be your time traveling times your average speed traveled, right? So that's your daily average travel distance. Then we kind of believe that there's an average gas mileage, right? The number of gallons you can go in a mile. So that from there, we can say, what's the daily average gas usage, okay? Then if there's an average number of gallons per fill up in your gas tank, if we can write down the average gas tank size, then we can write down how many fill ups there ought to be in order to allow people to travel however fast travel however fast and however far they're traveling, right? And then that's daily average fill-ups per person. Then multiply it by N, and that gives you the total number of fill-ups per city. And then if we know how many fill-ups you can have in a day, then that gives us the total number, or the minimum number of gas pumps you need in a city if every gas pump is perfectly efficiently used, like it was during the 70s oil crisis, and we might start to see next week. Right, so that gives us a sort of relatively simple way of describing the relationship between speed, the speed that we think people travel, and the number of gas pumps you need to see in a city. Well, we have a lot of census data on how many gas stations we see in a city. So these two things ought to be the same, that we from the sort of Luisia's original papers, we know that gas stations scale with n to the 5/6 like many other forms of infrastructure, that there's fewer gas stations per capita in a big city compared to a large city. And that means, like, this is just then a little algebra to say that then we think that speed ought to scale with n to the minus 1/6, which means, this isn't going to be shocking to anybody, when you're in a bigger city, you travel a little slower. Not a lot slower, but a little bit slower. Systematically, with the bigger the city is. So sort of that's my derivation on how I think speed is going to scale with city size. Now, I know anybody who cares about public transit is going to say you're wrong, because public transit exists. And so far, in this lens, I haven't figured out a systematic way of thinking about how to incorporate public transit into this lens, which is why this is work in progress. But that's sort of where I'm at on trying to sort of fill in each of these little boxes and eventually get to a theoretically defensible characterization of the relationship between interactions and city size. Good? Questions? One of the things that I've done to sort of try to convince myself that I believe my speed result, because everything is wrong until you've convinced a little better, I pulled some data from Texas A&M University on, they have a bunch of sort of statistics on travel, on vehicle travel miles. So they have freeway miles and arterial miles, do some math, and you can get a characterization of speed. It did not work out as nicely as I wanted. This looks like a spaghetti plot because it is. These, I don't know if you can read the coefficients, but the slope here is statistically indistinguishable from 0. One of the reasons I think that is the case is that their data is looking at the urban area, and my lens for what a city is includes the full metropolitan statistical area, which excludes less dense places in urban environments. And those less dense places probably have a lot of the miles traveled, but less of the delay, right? Like, you spend your time stuck in traffic in the center city, and this is missing this data set is missing all of the sort of drive from out in the outskirts from home into where you're almost at wherever you're going. And that hypothesis is supported by their statistics on delay. Because most of traffic delays probably do happen in the urban parts of cities. You're stuck in traffic where all the other people are. And that's just not a nonsense plot. There's a nice, like, you can see an increasing relationship there, which is saying that delay aggregate hours spent waiting in traffic scales superlinearly with city size over I think this is a 30-year panel data set. So here's another, then we can move into the ORNL data. One of the ways that I talk about human mobility is we have our first spaces. This is where we go home. Our second spaces, which is work and school, that's where more or less we all are right now. And then there's third spaces, leisure, coffee shops, shopping, entertainment, civic engagement, whatever. There's really good data from the census on first spaces. There's good data on work and school and so on. There's horrible data on what we do with our leisure activities. Third spaces are often just ignored in how we think about human mobility and how we think about social interactions when we try to model them. So this is, what happened there? This is ORNL data. This is now the ORNL data, where they took their device level traces, transformed it into transformed it into an inferred social network. And then we can look at the number of nodes and edges. The ORNL data does include third spaces, which is good because that's the thing that we can't measure. And then we pulled data from a scientific data paper that they've made a synthetic social network, but only for home and work, or homework and school. They exclude any kind of leisure activities, which isn't how people actually behave, but is sort of the best that a lot of places can do. And that's that's often how epidemic modeling is done, which I think is a problem. And then this is sort of imagining to be one day. The ORNL data is imagining it's over 90 days.
Question. So are you able to control, sure, our devices are nearby for 1 hour. Are you able to control if I'm in social media or working or doing something that then therefore would break that interaction between?
No. So we're just saying co-location, that like your physical devices and by inference your physical bodies are nearby for a long time, which is necessary but not sufficient to have actually interacted, right? Like there's co-locations, then there's maybe we actually talk to each other, and then there's like maybe we're actually friends and had an interesting conversation, which gets smaller and smaller and smaller. Yeah, and so the relationships modeled in the Jiang synthetic data probably are real. I mean, they represent more real relationships, but we also have real relationships outside of work and school. Every one of us, to stay sane, does. But there's sort of some problems that have come up with this is that the ORNL data, even though it's huge, it's also highly sampled, right? It's only a 2 to 5% sample of the city, which for network statistics breaks a lot of things. The Jiang data lacks the third spaces, and then they don't align in time, which is how we sort of tried to downscale the Oak Ridge data to represent 1 day instead of 90 days by assuming that every edge has a 1 in 90, every edge that occurs every interaction that is measured by Oak Ridge has a 1 in 90 chance of showing up in our sort of version of in our 1 day version of the Oak Ridge network. Okay, so here's the sort of total statistics, right? New York City has almost 2.5 billion edges in their network, which, right, like is huge and is still only a 2% sample of New York City for those 90 days. Gadsden, Alabama has 1.2 million edges in their network. And is about a 5% sample of the whole city. So we're sort of trying to reason through what it means to make inference when we have a big data set, but also a very highly sampled data set.
So the number of edges, does it scale with population or density or kind of a combination of both?
Because population and density systematically scale from the literature, I'm only trying to measure it in terms of population. An interesting question in the literature is to what extent do things like density or other characteristics of cities that we might know about, you were talking about sort of whether they've been planned atomistically or holistically, whether that influences the scaling residual, which I think is a really interesting open question. Mm-hmm.
If a person's phone is only in the data for 1 day and not all 90 days, does it make it in that sample, or it has to be there all 90 days?
45, it has to be there, it has to throw off data 45 out of 90 days. So these are, mostly people who manage to be in this city for at least half the time. We had an interesting vignette on Indianapolis that, if I have time, I'll tell you all of our wonderings about Indianapolis.
How do you deal with like the 30-meter bubble with like tall buildings? I can imagine you're going to be within 30 meters of a lot more people in a 60-story apartment building.
Yeah. That is a substantial concern because if you just sort of and that's also something that's going to scale with city size, right? Like Gadsden, Alabama does not have 100-story buildings, but New York City has a bunch of people living, not 100-story buildings, but New York City has a bunch of people living in high-density places. And yes, this version of the world collapses everybody to the ground floor. That is something that we hope to figure out what to do, but I don't know what to do about that yet.
The nodes here, are they the physical structures?
They're devices.
Devices, okay. Nodes are moving.
Yes.
Okay, all right.
Okay. Yeah, and so sort of the two strategies, this is a dumb strategy, and I'm presenting it only to sort of outline what dumb is. But I've taken sort of two other strategies to try to sort of get a first pass at thinking about how we address the network sampling problem. The dumbest strategy is to just declare that there isn't a network sampling problem, that our observed data is reality. That's dumb, but we can do the math on it anyways. The next, one approach that I think is at least semi-sensible is to imagine that we have a full population and we got to our sample by just randomly selecting devices out of our sample. If that was the sampling procedure, then any edge has, with probability pi, to sort of articulate my math here. If we randomly select nodes from our full population with probability pi, then an edge will stay in the sample procedure if both of its endpoints got picked. And that's going to be pi squared. That's basic probability. So this line is how we would correct our number of edges based on the number of nodes if we were perfectly randomly sampling nodes from the true population. Then what I also wanted to do was suppose instead of randomly sampling on nodes, we were randomly sampling on edges, because edges in this world are a physical place where two devices were co-located, right? So like it's reasonable to imagine that we might be sampling on edges. That might be part of how data got into our system. I tried real hard to come up with a really good proof of how one would back out the true number of edges from the observed number of edges given a known sampling rate on nodes. I couldn't do it. I think, but I'm not 100% sure that it actually can't be done without more information, because you also have to make a bunch of assumptions on how the network was generated. But if we assume that the node sampling rate is the same as the edge sampling rate, which it's not, but I needed to do something, then this is the way you would back out the true number of edges from the observed number of edges. And so there we can sort of replace our true edge numbers with how we would model them based on sort of an assumption of how we do the sampling. Mm-hmm.
Okay, so I'm trying to think of the edges, because you had mentioned that there could be node at different strata, more like if there's like a building,
Mm-hmm.
there's a node, and there's edges should stand for co-location. So what if there are like node on the first floor and there's a node on the second floor? Won't it see it as?
Yeah, this version of the world will see if two phones are on top of each other, this version will see them as co-located, which is wrong.
Okay. So how do you?
So far, I haven't.
Okay.
But it is a very good point.
Does a node get counted can a node have more than one edge?
Yes.
So anyone who it's co-located with, it would then be repeated in the data, but it would have a unique edge.
Yeah, so like the way that we understand the data generating, if all of us here have all of our phones and we're within 30 meters, and I'm going to talk for a long time, so you're stuck with me. So there would be, there's 30 people here, say, and so there would be 30 times 29 unique edges created by this talk, because each of us would get an edge to each of every other person, because we're all at the same stop point. And that's ignoring the fact that we are also on the 5th floor of a building.
So to be included in the sample, you don't have to have the same edge you don't have to have the same two nodes. You just have to be a node in the system.
Yeah, to end up in our sample, you do need to have, we remove isolates. So a node, a device that throws off data for 45 days, but never meets the criteria for creating an edge, we exclude. Okay, so then from there, it's pretty simple statistics to estimate the scaling exponent. under, all these sort of different ways of seeing the world. The Jiang data, as expected, is linear. There's no need to resample on nodes and edges because they have the same, they're constructed to have the right number of people. And it's linear because that's how they constructed their data. For epidemiological modeling, that's a problem because interactions are what transmit disease. But any way I've figured out how to slice these data so far, even though absolutely there's problems with how we're doing this, they're all super linear and sort of that's strongly statistically significant. Yeah, I didn't put this I didn't put the uncertainty bounds on here, but it is. These numbers are a lot bigger than 1, which is sort of what we'd see from a null result. And then from there, I'm nervous about this, right? Because of the things that you brought up, right? That we're not sure that this is a good way of representing networks because it's really hard to understand what's happening in a network when it's as highly sampled as these networks are. But I think we can say something really useful about the distribution of interactions among individuals because that's not a network problem. So we've got, in New York City, we've got 500,000 imperfect records of who New York, or how often New Yorkers are interacting with other people. So we can think about the city level interaction frequencies and then also the distributions of interactions of individuals. So here's the citywide averages. The way this is structured is each donut is one of my cities. Darker green are more frequent interactions and lighter green are less frequent interactions. And this is for 9 of our 10 cities. And what we're seeing, and this is sort of average, so counting up all of the interactions that happen, perhaps you and I interacted 10 times, and you and I interacted once, and you and I interacted 100 times over this, or were co-located 100 times over the course of this 90-day window. Then you can add all those up and look at the distribution of how many total encounters were within pairs who interacted daily or weekly or monthly or with whatever frequency, right? And so one of the things we can see is that a greater share of the total interaction in large cities comes from infrequent contacts rather than from frequent contacts. And that's sort of the opposite for the small cities. So the big cities, little cities, they go up like this. And then smaller cities have a greater share of their total interactions arising from frequent contacts, people you see all the time. That's just what the data says so far, which is consistent with the sort of urban scaling theory that bigger cities foster novelty. When you've got a bunch of people closer together, it's easier to find novel stuff to have interactions about, or people you haven't met before. And then this is only to sort of demonstrate that I did the work. I pulled out the distribution for the least social person in every city, and really it is the device, what this actually is the device with the least number of edges. But the least social person in every city interacted with one person once in 90 days. Because if they didn't have one edge, they wouldn't have made it into the data. So really this is just sort of a data limitation. But it's all the same as we expect. Then you can look at the distribution of sort of your typical person. So what I did here was I ordered all of the devices in my city network by the total number of co-locations that they had, and then put them into deciles. So my middle decile, and then just to make the computing work, I randomly pulled 100 people out of my middle decile and averaged their distributions of how many times they interacted with somebody else. And you still sort of, and lighter colors are the sort of infrequent interactions, darker colors are the more frequent interactions. And you can still sort of see a pattern that larger cities have a greater share of repeated interactions. Or you sort of see the pattern that larger cities have a greater share of interactions. Then when you look at the most social people, you find kind of the opposite result of the median person. So it's the same sampling procedure in that I binned the population into deciles based on their total number of interactions and then randomly pulled 100 out of that top decile. So these are the super social people, not the absolute most, but the social people in all of my cities. And the trend, like I said, is sort of opposite for the middle. Larger cities have a greater share of interactions that are novel compared to Gadsden, Alabama, where all of their interactions with people they see on a regular basis. Or not all, but more. So that's sort of how I'm right now, how I'm trying to tease apart the data and how I'm trying to start to systematically understand how we think about heterogeneity, in this case, in interaction patterns in cities, in order to sort of say something sensible about how we can think about interaction patterns to test the hypothesis that underlies urban scaling theory, and then move urban scaling theory as a whole from only city level averages to being able to characterize within city heterogeneity. Okay, so like this work is half done, so that's fine. But like, let's imagine that I have a nice polished paper and everything is done. Sort of some of the best case outcomes would be sort of, to what extent is scaling theory supported by data? Can we characterize heterogeneity in a systematic way so that we can say something theoretical or predictive about how we observe behavioral heterogeneity in order to use it for something? And then in sort of what I really hope to get to is being able to map between heterogeneity in our social processes and heterogeneity in our built environment, because then we can go back and forth between one or the other, depending on which one we can measure for that particular purpose. There's some applications: disease forecasting, earth system hazards, conflict and risk. Those are other things that I work on in other projects that in the best version of this paper self, it might be useful for. Yeah. Questions on that, and then I will briefly talk about flood risk.
How would a disruptive event like something like COVID impact this scaling theory, or is it looking at it on such a sort of zoomed out, broad scale that it's just going to be like a small blip? If you squint at the time speed data that I flashed up real briefly, you could see a very statistically significant effect of COVID on speed. That lots of people, there were many fewer people driving, so delay hours went almost to zero. That was an easily observed thing. Andrew, my SFI colleague who I'm working on this with really closely, also has a paper looking at disease attack rates in the sort of first and second COVID waves, and there's a strong observable scaling effect of disease, which is what we expect from sort of the idea that there's more interactions and more interactions in cities, so there's more potential for disease to transmit. And his paper is an empirical approach showing that. So I think that urban scaling theory has been well tested enough in enough context that sort of drives how whatever big event filters down to all of us in a city. It mediates the event rather than like breaking scaling theory, except for my diphtheria paper. Okay, I will talk about. Sorry, I took up too much time on the part that I'm really excited about. So I will go through this fairly briefly. This is a paper published a couple weeks ago, based on a project in Southeast Texas, the one for which I'm using futures. And what we've done here, the sort of core, the initial genesis for this project was we're working closely with a bunch of water managers. We got money for new flood sensors, and they wanted to know where to put them. It's a simple question, and here's a very long answer to that simple question. One question is sort of what makes a good observation system, and then we think about risk as resulting, in this case, from interactions across multiple systems, and then flood observation systems serve a bunch of purposes, right? Like they can be useful for emergency response or infrastructure planning. They can also be useful for scientific insight. Here's Southeast Texas. It floods. It's really flat. Here's a map of our study area. And then what I used to characterize flood hazard here was FEMA flood risk, which is a terrible way of characterizing flood risk, but it's what I had. Here's the data that we're using on socioeconomic characteristics. A colleague of mine took census data and downscaled it to the individual household level, probabilistically downscaled it to the household level, and probabilistically inferred, and it adds up so that at the block group level, households have sort of the right number of risk characteristics, where you folks have used social vulnerability indices before? Yeah, okay. The sort of indexes of social vulnerability that we're using here are race and ethnicity, whether you're white or not, non-Hispanic white or not. How income below the regional median, homeowner or renter, and I'm forgetting one, sorry. And then we also had to organize space in a hydrological way because we're worried about flooding. So these are very high resolution. They're not quite catchments, but we sort of define them as the land area that's most closely related to whatever might be observed by a particular flood sensor. I'm zooming in on here because this is where the interesting results are going to be. This is a place called Bridge City in Orange City, just to tell you the future up front. And you can think about a household if they're in a sensor catchment or not, and if they're in a FEMA flood zone or not, right? Like that's easy, that's a binary. So this is sort of the color scheme that I'm using for a while. Households that are not in a FEMA flood zone and are in a sensor catchment area, they're measured, they're observed in the context of knowing whether flooding will be happening or not, but it's sort of extra, right? Households that are not in a FEMA flood zone and not in a sensor catchment area, that's fine. We don't think they're going to flood. Households that are in a flood zone and are in a sensor catchment area, that's the best we can do in this universe. And then this purple area are the places where we really ought to think about expanding our flood system. So here's how that looks played out among given the sort of hydrology and what we know about people in the area. And it works out that the more, I'm sorry that my images turned out so bad. The more vulnerable people, those are the folks out here, are also more likely to be be outside of a flood zone and in a sensor catchment area. So like usually we talk about the co-location of vulnerability of sort of socioeconomic vulnerability and vulnerability to natural hazards. That's a very common pattern, but it's not what we saw here. Just isn't. You can do that empirically too. And then we can think about risk. So risk we think of as a confluence of hazard, exposure, and vulnerability. This is a very, very normal framework that people use. So we can think about risk to people from flooding, and then we can sort of specifically characterize each of these wings of hazard, exposure, and vulnerability. You can write it down. Probability of flooding times the area of your pixel gives you the probability that this specific pixel is going to flood in a given year. You can think about exposure, do more or less the same math, but instead of looking at the area within a catchment that will flood, you can look at the number of people. This measures the number of people in a catchment that will flood. Then you can add the population characteristics. If we had perfect data, which again, we don't, but if we had perfect data, what I would want this to be would be the expected economic losses to a person, to a household from having their home exposed to flooding. We don't have that. We'll never have that. So the social vulnerability data that I'm using is the best available proxy I could come up with. And then you can add those up, right? Like risk then is the confluence of all three of those things. For a decision maker, you can talk about how important it is to understand flooding of land or flooding of houses or the consequences of flooding. And you can put little parameters on the front, and then a decision maker can have a little widget that weights these differently. And then that'll give out a different level of risk depending on which aspect of the system they think is most important. And then we can make a map of how much risk there is, or how much the value of each of these different things in every catchment in our area. So sort of greater purple is more a greater expected flooded area. In this lens, I turned gray the catchments that already have a sensor in them because we don't need to worry about expanding our sensor network there. It's duplicative. But like lots of flooding is on the coasts, as we expect from flooding. Then when you add people, though, we're not so worried about the coast because there's no people who live there. The people who are exposed to flooding are up in Orange County here, Bridge City and Orange City. And that sort of instantly changes the conversation when you're suddenly saying, oh, well, maybe I care about flooding of people, not just flooding of wetlands, which is what's supposed to happen. And then if we had perfect data, this would be flood losses. We don't, so it's some proxy for flood losses. So thinking about, okay, well, let's try to understand flooding of people who we think are most vulnerable to flooding, because we think their socioeconomic losses will be higher. That's And that still tells us more or less the same answer that we saw from just population density. But it could be different. And that gives us sort of an overall perspective on how to reason about flood losses, how to reason about where flood losses are high, and therefore where we ought to think about putting in flood sensors so we can better understand the system. Now, what this has done so far is said, our goal is to understand the maximum risk. That's a reasonable goal, right? Particularly if you're worried about emergency response or sort of planning or whatever. But if your goal is scientific insight, sort of understanding the behavior of the system as a whole, it's a bad idea to only measure the high-risk places, right? Because we want to have an understanding of the whole system so that we can infer the behavior of anywhere from what we've observed already. And so this math is saying, if instead of maximizing observed risk, we want to ensure proportional observations across any of the input data so that our observations are representative of the whole system, here's what we would do, and we can use sort of the same basic idea of hazard, exposure, vulnerability, add it up. Again, the decision makers can have a little parameter there and a little widget that they can use to weight the different aspects of risk, and that's a different way of thinking about how one might reason about where we ought to put flood sensors in order to sort of think about water risk in this particular system. And then this is, my image resolution is terrible, I'm sorry. But under here, the green is where, if we were gonna put in 10 sensors, the green is where we would put 10 sensors if our goal was to maximize the how well the observation system represents the system as a whole. And purple is where we would put them if we wanted to just observe as much risk as we possibly could given our sensor budget. Yeah, and so this is a sort of framework that's like, I applied it in Southeast Texas for the purposes of understanding flood risk to people, but you could swap out any arbitrary hazard layer and use the same framework when you're sort of trying to think about how you reason about risk, about interactions between physical risk and consequences to people. Yeah, thank you.
Yes, we have a few minutes for additional questions.
How do the decision makers get the ability to do the weighting? Like, how do they actually engage with that product?
Yeah, I made a little widget. This project, or the Southeast Texas project, was a $25 million project where I was one of, I don't know, 30-ish people on the project, working closely with a group of water management professionals, and we had other stakeholder groups too. I wasn't in charge of the co-design, but like I kind of interfaced with them. And so what I did was I made a little HTML widget that like showed each 3 layers of the map. And that's online now. And then I also, it didn't work very well, so it's not online anymore, but I made a little, our shiny dashboard where you've got a slider for each of the different alphas. Mm-hmm.
Really nice presentation, I appreciate it. And you presented on these urban scaling laws, and some really interesting kind of general equations that can come out of them that can model different urban settings. And a lot of the data that you're using, these kind of connectivity data, it's like they're large but messy. So I'm wondering if there's any information you can borrow from other like biological systems, like simpler systems, maybe like ants, ant hills, or other like kind of social animals that could help inform these kind of social scaling laws, or if you've considered that.
Yeah. So the intellectual precursor to urban scaling laws were biological scaling laws. And so there's a book by a man named Jeff West called Scale, where Jeff West was in the 90s, I think, was working very hard on what he then called allometric scaling of organisms. And so in biological context, the scaling exponent tends to be what he calls quarter power. He's this very old British man, so I can't say it without trying to mimic his accent. But he talks about quarter power scaling, that like metabolic rates and
and energy-related kinds of things tend to scale superlinearly a quarter above 1, whereas in urban environments it's the sort of sixth, it's 1/6 above 1. So there's like the math is the same. The analogy to reality is very similar. There's just more aspects of the system. Jeff motivates his biological scaling with looking at physics of like, if you have a column, the sort of force that a column can, going between the weight of a column and the strength that its sort of capacity to withstand load, I think that's 1/3 if you like work out the physics. So yeah, he starts with physics and then moves to biology. And then Luis Betancourt, who is my postdoc advisor, did most of the, Luis and Jeffrey worked together on the innovation around urban systems. Yeah. Yeah.
So we're past 4, so let's give Christa another round of applause.
Thank you.